Hello everybody, welcome to Shaders Monthly. Today we are going to talk about tangent space normal mapping. A normal map is a texture that is applied to a mesh to add detail to its geometry. This means we can use fewer triangles and can provide the details of the geometry using a normal map texture. Here you can see a 3D mesh of a stone demon. On the left we have the original high poly mesh with more than 30 million triangles. On the right you can see a low poly version with 30,000 triangles. Let's zoom in such that we can see the individual polygons of the high poly mesh. As you can see on the left, there's a huge number of polygons, whereas on the right there are much fewer. If we switch from wireframe shading to surface shading, it is quite obvious that the low poly mesh has much less details. All the fine wrinkles and skin details on the left and a rather smooth surface on the right. However, when we add the normal map, which is shown on the bottom right, to the low poly mesh, we get a rendering result with many fine details. Again, this is the low poly mesh without the normal map. This is it with the normal map. This is impressive because visually the two meshes look very similar, even though the low poly mesh is much faster to render. Okay, let's start with the theory behind this technique. Later in the video we will implement normal mapping in GLSL. We begin with object space normal mapping. On the left you can see an example of a high poly mesh, and on the right its low poly version. Both meshes are given in their local object space. The red dots are the vertices and the blue arrows represent the provided per-vertex surface normals. As we have already discussed in previous episodes of Shaders Monthly, the rasterizer in the OpenGL pipeline interpolates the per-vertex normals, and we get an interpolated normal for each output pixel. These interpolated normals are visualized as the light blue arrows in the figure. Because of the interpolated normals, the surface appears smooth. This means we perceive a smooth surface, though the underlying geometry is much coarser. The perceived smooth surface is indicated in the figure by a yellow line. The interpolation can be done for the low poly mesh as well as for the high poly mesh. To use normal maps, the low poly mesh must also have per-vertex texture coordinates. The per-vertex texture coordinates can also be interpolated, and we get a mapping from each pixel of the normal map to a location on the low poly mesh. The high poly mesh from the left is now shown here on the right. Now we perform the so-called baking of the normal map. There are different approaches for baking. The approaches differ in how they ensure that we hit the right location on the high poly mesh. The most basic approach is that we follow the direction of the interpolated normal of the low poly mesh inwards or outwards until we hit the high poly mesh. At the hit location we read off the interpolated normal of the high poly mesh and store the result in the pixel of the normal map. However, we need to take care because the x, y and z coordinates of the normal are in the range from -1 to 1, and we can store only values from 0 to 1 in the RGB color channels of the normal map. Therefore, we multiply by 0.5 to go from the range -1, 1 to -0.5, 0.5. Then we add 0.5 and are in the range from 0 to 1. Now when we render with the normal map, we perform the inverse mapping from the RGB values in range 0, 1 to normals in range -1, 1 by multiplying by 2 and subtracting 1. Instead of using the interpolated normals of the low poly mesh in the fragment shader, we read the normals from the normal map. This creates the illusion of a highly detailed surface. This approach is called object space normal mapping because the normals of the high poly mesh are stored in its local object coordinate system. This means that when we apply a transformation to the mesh, we need to transform the normals accordingly. As we have discussed in episode number 3 of Shaders Monthly, normals can be transformed with a 4x4 normal matrix, which is computed by the transposed inverse of the 4x4 mesh transformation matrix. This concludes object space normal mapping. Next up is tangent space normal mapping. The baking process is almost the same as for object space normal mapping. The only difference is that we do not store the normals in object space. Instead, we use a local tangent space, which we compute for each surface location. Here you see the low poly mesh again. The blue arrows represent the per-vertex normals. The light blue arrows are the interpolated per-vertex normals. And finally, the arrows with the greenish-blue color are the high poly normals that we want to encode. So for each vertex we are given a per-vertex tangent space. We will talk about how to calculate this per-vertex tangent space soon. For now, let's assume that this per-vertex tangent space is given to us as an additional vertex attribute. The red, green and blue arrows here represent the x, y and z axes of the coordinate frame. Most importantly, the z-axis of the tangent space coincides with the surface normal. In the same way as we can interpolate the normal, we can interpolate the other axes of the coordinate frame for each pixel. Next, we get the high polynormals from the same baking process as before, but now we store the coordinates of a normal in the local tangent space. So, for example, this high polynormal here has this tangent space, and therefore, relative to its tangent space, the normal direction offset would be this. Again, we need to perform the same linear mapping from the x, y, z coordinates of the normal, now in tangent space, to an RGB color by multiplying by 0.5 and adding 0.5. We do this for every pixel of the normal map. And the creation of the tangent space normal map is done. Now, when we render with the normal map, we need to invert the process. We apply the inverse mapping from the RGB values in range 0 to 1 to normals in range -1, 1. Then we transform the normal using the interpolated tangent space and get back the desired high polynormals. The advantage of using the tangent space instead of the object space is that the normals are stored relative to the local surface orientation. This means that when the surface is deformed, the tangent space and the high polynormals will be deformed with the surface. Let's look at an example. At the top you see the low poly mesh without a normal map. In the middle is the low poly mesh with an object space normal map. And at the bottom the low poly mesh with a tangent space normal map. For this example, the object space normal map is very colorful because the normals are pointing in very different directions in object space. In contrast, the tangent space normal map is bluish. This is because the high polynormals have the overall tendency to point roughly in the direction of the interpolated surface normal, which is the z-axis of the tangent space. And as we know, the z-coordinate is encoded in the blue channel. Right now we don't see any visual difference between object space and tangent space normal mapping. This is because the mesh is not deformed. It is in the same position as it was during baking. If we now deform the mesh, we see the advantage of tangent space normal maps. When the surface is deformed, the tangent space deforms with it, and the tangent space normals are correctly applied. In contrast, the object space normals do not take the deformation of the surface into account. This is especially obvious here at the upper leg of the stone demon. As we see in the version without a normal map, the specular highlight on the upper leg should not be there if the light is coming from the front. So this is correct for tangent space normal mapping, but wrong for object space normal mapping. Another advantage of tangent space normal mapping is that a generic normal map can be applied to any surface. Here you see a tangent space normal map with some geometric shapes. We can apply it to different surfaces. Because the normal offset is defined in tangent space, it works on each surface. Now, before we can talk about how to compute a per-vertex tangent space, we need to talk about how to calculate a per-triangle tangent space. On the right you see a 3D mesh in its local object space. The 3D mesh is composed of triangles. For example, I have marked this blue and yellow triangle here. The vertices of the triangles are marked red. A prerequisite for calculating a per-triangle tangent space is that each 3D vertex with coordinates x, y, z has a 2D texture coordinate st. We have discussed texture coordinates in episode number 5 of Shaders Monthly. As we know, the texture coordinates s and t are in the range from 0 to 1. The texture coordinate system, given here by the red, green and blue arrows, defines the reference tangent space. By definition, the s direction of this Cartesian coordinate system is the tangent, and the t direction is the bitangent. And there's a third dimension that is indicated by the blue arrow pointing towards us. It represents the direction of the surface normal in tangent space. So the normal is perpendicular to the tangent and the bitangent. And the tangent and the bitangent are also perpendicular in our reference tangent space. To compute a per-triangle tangent space, our task is now to find out how the vectors tBn from the reference tangent space are mapped to transformed vectors t tilde, b tilde and n tilde, which span the per-triangle tangent space. We know that n tilde must be equal to the surface normal of the triangle. T tilde should point in the direction of a change of texture coordinate s in the 3D object space of the triangle mesh. B tilde should point in the direction of a change of texture coordinate t. This means if we follow t tilde here, we go in s direction in the reference tangent space. If we follow b tilde, we go in t direction in the reference tangent space. If we knew t tilde, b tilde and n tilde, we could set up a 3x3 matrix where the column vectors are t tilde xyz, b tilde xyz and n tilde xyz. This matrix transforms any normal direction in the reference tangent space to a normal direction in the per-triangle tangent space. This would give us a per-triangle tBn matrix. For example, this blue triangle here has a different normal than the yellow triangle, and the tangent and the bitangent also point in a different direction. If we follow t tilde here, we go in s direction in the reference tangent space. If we follow b tilde, we go in t direction in the reference tangent space. As a side note, we typically have used 4x4 matrices to implement transformations. However, here a 3x3 matrix is sufficient because we are only interested in the mapping of the axes. The origin of the coordinate system is not affected. Our transformation does not have a translational part here, but just produces a change in orientation. Alright, to compute the per-triangle tBn matrix, we need t tilde, b tilde and n tilde. N tilde is known because it is given by the surface normal of the triangle. To compute t tilde and b tilde, we first need to introduce some notation. The vertex positions in 3D object space for a triangle are v0 tilde, v1 tilde and v2 tilde. The texture coordinates for a triangle are v0, v1 and v2. Let's consider the edge E1 in tangent space between v0 and v1, which is given as v1 minus v0. And then the edge E1 tilde in 3D object space between v0 tilde and v1 tilde, which is given as v1 tilde minus v0 tilde. With known E1 tilde and E1, we can create a constraint for the unknown tBn matrix. The unknown tBn matrix must transform the edge E1 in reference tangent space to the edge E1 tilde in 3D object space. Let's try to use this constraint to compute t tilde and b tilde. It is important to note that we can only use the tBn matrix with edges and not with vertex positions, because the tBn matrix can only transform directions from one space into the other and not points. Here is the constraint equation again. We substitute the known coordinates for the edge in 3D object space and the edge in the reference tangent space. When we rewrite this matrix vector multiplication, we see that the unknown tangent vector is multiplied by S1 minus S0, and the unknown bitangent is multiplied by T1 minus T0. This gives us three equations for the six unknowns T tilde xyz and B tilde xyz. Therefore, this equation system cannot be solved. However, when we use a second edge, E2, between V0 and V2, we get three additional equations. Now we have six equations and six unknowns, and the equation system can be solved. We rearrange the upper equation for T tilde and the lower equation for B tilde. Now we can insert B tilde here and solve for T tilde. And we can insert T tilde here and solve for B tilde. This gives us the closed form solution for the tangent T tilde, and here's the solution for the bitangent B tilde. However, notice that we are dividing by this value d here, so it must not be 0. We call this value the determinant, and it's calculated directly from our texture coordinates. Geometrically, you can think of it as the area factor. It is proportional to the signed area of the triangle in texture space. The only time this value becomes 0 is if the triangle is degenerate. That happens if the three vertices fall into a straight line or sit on the same location, causing the texture area to collapse. The determinant d will be important later, because we can detect by the sign of the determinant if the transformation from the reference tangent space into the per-triangle tangent space is orientation preserving. In our reference tangent space, we used a right-handed coordinate system. If the determinant is larger than 0, the transformation into the per-triangle tangent space is orientation preserving. In this case, we stay in a right-handed coordinate system. For the right hand, the thumb points towards the tangent, the index finger towards the bitangent, and the middle finger towards the normal. However, if the determinant is smaller than 0, the transformation is not orientation preserving, and we get a left-handed coordinate system. Again, the thumb points towards the tangent, the index finger towards the bitangent, and the middle finger towards the normal, but now for the left hand. Okay, this concludes how we can compute a per-triangle tangent space. Next, we want to compute a per-vertex tangent space. Nowadays, the MikkTSpace approach is the de facto standard for generating a per-vertex tangent space. It was proposed by Morten S. Mikkelsen in 2008 and has since been adopted by most 3D applications. We need a standard because it is important that the baking tool and the renderer uses the same approach to generate the tangent space. Otherwise, this will lead to mistakes in the resulting normals. We will now discuss the MikkTSpace approach briefly in the following slides. A link to the reference C code can be found in the video description. Let's assume that this vertex in the center is the vertex for which we want to compute its tangent space. We have calculated the per-triangle tangent space T tilde, B tilde, N tilde for all triangles that share this vertex. Now we want to calculate the average tangent space for the vertex T bar, B bar, and N bar. Obviously, an average tangent space is only required if we want smooth shading at the location of the vertex. If we want hard edges, we can simply duplicate the vertex position for each adjacent triangle and use a per-triangle normal and a per-triangle tangent space. Usually, the smooth normal direction n bar for the vertex is already given to us from the input mesh. So the task is to calculate the average tangent T bar and the average bitangent B bar. To solve this task, the MikkTSpace approach first performs a Gram-Schmidt orthogonalization. The Gram-Schmidt orthogonalization works as follows. Given vectors n and a, the Gram-Schmidt orthogonalization applies a small offset to vector a to make it orthogonal to n. Thereby we assume that the vector n is normalized to have a length of 1. Orthogonal a equals a minus an offset vector. This offset is the dot product of n and a, which gives a scalar factor, multiplied by the vector n. As shown in the figure, the dot product of a and n gives the length of the projection of a onto n. Multiplying the dot product of n and a by vector n results in a vector of that length in the direction of n. Subtracting that vector from a gives the orthogonal a. The MikkTSpace approach calculates the per-vertex tangent space t bar, b bar, and n bar by computing a weighted average over the adjacent per-triangle tangent spaces t tilde I, b tilde I, and n tilde I, where I indexes the involved triangles. First, for each triangle I, we use the Gram-Schmidt orthogonalization to make the per-triangle tangent t tilde and bitangent b tilde orthogonal to n bar. This orthogonalization can also be interpreted as a projection of the per-triangle tangent and bitangent onto a virtual 3D plane with surface normal n bar. Next, we compute the weights that we use for the weighted average. Here, the MikkTSpace approach uses orthogonalization again to project the two incident edges E1 and E2 for each triangle I onto the plane with surface normal n bar. Then we compute the weight Wi, which is given by the angle between the projected edges. The angle can be computed by the arc cosine of the dot product of the projected edges. We divide each projected edge by its length to normalize the vector to a length of 1. Finally, we compute t bar and b bar by taking the weighted average over all adjacent triangles indexed with I. The tangent t bar is equal to the sum over all I, wi times the normalized t tilde I perpendicular, and accordingly for the bitangent b bar. The MikkTSpace approach specifies 4 rules when to include a triangle into the average. Triangles are only included in the average if they, first, share a vertex. This means that both triangles have a vertex with the same 3D position. Second, have the same vertex normal at the shared vertex. This criterion checks if we want smooth shading at the vertex location. If the normals are the same, the tangent space should be averaged. Otherwise, the rule ensures that at edges with different normals, the existing hard transition of the normals and hard transition of the tangent spaces are maintained. Third, have the same texture coordinates at the shared vertex. If the texture coordinates are not the same, it is assumed that the triangles are not part of the same surface parameterization. In the figure we see an example. The same vertex in object space has 2 different texture coordinates. This one for the triangle group marked in yellow and this one for the triangle group marked in purple. So in this case we would need to calculate 2 different per-vertex tangent spaces by taking the weighted average over each triangle group. 1 tangent space for the yellow group and 1 tangent space for the purple group. Fourth, have the same sign of the per-triangle determinant d. This rule ensures that we do not include left-handed and right-handed tangent spaces into the same triangle group. Here is an example. The yellow triangles have a positive d, indicating a right-handed per-triangle tangent frame. The cyan triangles have a negative d, indicating a left-handed per-triangle tangent frame. This means that the yellow and cyan triangle groups are not part of the same surface parameterization and we must compute a separate per-vertex tangent space. This one for the yellow group and this one for the cyan group. Because of Rule 4, a vertex with the same position, normal and texture coordinate can nevertheless have multiple per-vertex tangent spaces. In this case, a vertex may need to be duplicated multiple times to accommodate the different tangent spaces. Consequently, if your rendering engine uses an index list to address vertices, these additional vertices must be taken into account. Thus, the index list must be updated after a tangent space is added as a vertex attribute. We computed the per-vertex tangent and bitangent in such a way that it is ensured that they are both orthogonal to the per-vertex normal. However, the tangent is not necessarily orthogonal to the bitangent because this was never enforced in the algorithm. To generate an orthonormal tangent frame for normal maps, the MikkTSpace approach simply drops the computed bitangent and recomputes it from the tangent and the normal. We get the final orthonormal per-vertex tangent t bar prime by normalizing the computed average tangent t bar, and the final orthonormal per-vertex bitangent b bar prime by the cross product of n bar times t bar prime. The cross product is multiplied by the sign of the determinant d to form either a right-handed or left-handed orthonormal tangent frame. T bar prime, b bar prime and n bar give us the final 3x3 TBN matrix that transforms a normal from the reference tangent space to the object space. If we do not want to use matrix vector multiplication, we can also compute t bar prime times nx plus b bar prime times ny plus n bar times nz. As the bitangent can be computed from the tangent and the normal, we do not pass the bitangent as a vertex attribute. Instead, the tangent information is passed to the shader by a forvector tx, ty, tz, tw. The tx, ty and tz components provide the per-vertex tangent t bar prime and the tw component provides the sign of d. Due to Rule 4 from the previous slide, vertices of the same triangle have the same tw value. Alright, that concludes the theoretical part. We move on to the practical part and implement a tangent space normal mapping in GLSL. We use the GSN Composer at gsn-lib.org as our shader editor. The GSN Composer is a web-based tool that I created especially for teaching shader programming. But you can use any other shader editor as well. We write pure OpenGL GLSL code that you can use anywhere. Links to examples that execute the same shader code using C++ or Java can be found in the video description. The implementation is based on the example that we created in episode number 9. Click on Project and type in the name Shaders Monthly 09 and click on Open Existing. Then open the graph Microfacet BRDF and press Play in the Time Control panel. The example from episode number 9 uses a Microfacet BRDF and a directional light to render a stone demon. Here is the shader node that performs the rendering and contains the shader code. This input node contains the mesh data of the stone demon. Furthermore, we see that 4 textures are used: albedo, roughness, normal, and emission map. The mesh is illuminated by a single directional light source. The light direction can be changed here. We open the shader editor and inspect the shader code in the fragment shader. Down here in the main function we have the variable wfn, which is the interpolated per fragment normal in world space. Here we normalize wfn and assign it to n. In the next line we apply the normal map. Let's visualize the normal by assigning it to the output. outColor.rgb equals n. Now let's see what happens when we comment out the line that applies the normal map. As expected, the normals have much less detail. The current method for applying the normal map that we just commented out does not use the MikkTSpace approach. Instead, it computes a local per pixel tangent frame from the derivative of the vertex position and the derivative of the texture coordinates. This method is convenient because we don't need to pass tangents as vertex attributes. However, it is different from the MikkTSpace approach. Let's try to implement the MikkTSpace version. We go to the vertex shader and get the Per-Vertex tangent attribute. In vec4 tangent, input vertex tangent from mesh. We need two new out variables of the vertex shader. Out vec3 WFT, output fragment tangent in world space. Out float WFT sin d of the tangent space. Here is the 4x4 matrix mesh transform that is used to transform the vertex position from local object space to world space. And the 4x4 matrix mesh transform transposed inverse, which transforms the normal from object space to world space. We need to apply the same transformation to the tangent. WFT equals vec3 mesh transform transposed inverse times vec4 tangent xyz 0.0. The W component of the tangent vector provides the sign of the determinant, which defines the handedness of the tangent space. WFT sign equals tangent.w. On the MikkTSpace website, which is linked in the video description, it says, quote, "The baker in both Blender and the XNormal plugin will keep the vertex normal and the vertex tangent normalized in the vertex shader. However, in the pixel shader, the unnormalized and interpolated vertex normal and tangent are used to decode the tangent space normal." End quote. So if we want to follow these instructions, we need to add normalize to the normal and normalize to the tangent in the vertex shader. Next, we switch to the fragment shader. We add matching in variables to the new out variables. In vec3 WFT, fragment tangent in world space interpolated. In float WFT sin d of the tangent. We need the unnormalized and interpolated vertex normal. Vec3 n equals WFN. If true, apply normal map. We compute the bitangent. Vec3 WFB equals WFT sin times cross WFN WFT. We read the high polynormal from the texture. Vec3 high polynormal equals texture normal texture tc.xyz. Normal texture is the normal texture and tc are the texture coordinates. Next we convert from the range 0 to 1 to -1, 1. High polynormal equals normalize high polynormal times 2.0 minus 1.0. We use the TBN matrix to transform the normal from the reference tangent space to world space. N equals WFT times high polynormal.x plus WFB times high polynormal.y plus WFN times high polynormal.z. The final step is to normalize the normal. N equals normalize n. Apply code, play. Okay, this looks promising. Now instead of rendering the normal, let's show the shading output. Lin to RGB radiance. Apply code. Perfect, that's it. We have discussed and implemented tangent-based normal mapping. If you have any questions, please leave a comment or contact me directly. As always, the C++ and Java source code can be found in the video description. See you in the next episode of Shaders Monthly.